Thank you very much. As stated, my name is Andrew Smith of Bentley Systems. I'm the Rail Business Development Manager, and welcome to this Accelerate session as part of the AssetWise for Transportation, talking about turning data into actionable information. As has just been stated, this is the second of 3 sessions that are taking place. If you missed the first session by Russell Page, it is already available online with details you can see here. And session 3, looking at the next generation for strategic asset management for transportation, is here, will be taking place on Wednesday the 8th of January. So let's start with the obvious question, why asset performance? So when we're talking about turning data into actionable information, we're focusing in particular on asset performance, improving the quality, reliability and safety associated with our transportation assets. So asset performance and the challenges associated I split into 2 high-level areas, one of which is the challenges associated with new infrastructure and the other is the challenges associated with aging infrastructure. When our infrastructure first goes live, there are high expectations, of course, from the owner-operators, from all of the stakeholders, but also from the users associated with that infrastructure. If we have problems early in the life cycle of the asset, then the damage to reputation to us can actually take much longer to resolve than the actual problems that we encounter trying to rectify. So we need to make sure that we've got a very high quality asset. We need to pick up any snags we can as early as we can, and critically as well, we need to understand how the asset is behaving and whether it's behaving in the way we expect it to, so that we can then start being proactive about what we need to do to ensure that we can deliver a compliant quality service to our end users. As we get towards aging infrastructure, a range of other challenges start facing us as well. We often find that the requirements that we'd actually built the initial railway or road network to are changing over time, that we're expecting the system to be available for more hours of the day. We're expecting more vehicles to be running along it. We're expecting longer vehicles, heavier vehicles potentially, and all of this typically up against a budget that's either remaining static or is being reduced over time. Certainly in rail globally, there's tended to be a history of underinvestment whilst the asset's been milked, to be honest, and it's leaving it in quite an awkward position in terms of being able to carry on delivering a good quality, reliable service. All the time we're using this asset, it's deteriorating, and of course the more we use it, the more rapidly it's likely to deteriorate. We've got to balance maintenance versus renewals decisions that we make, and another key challenge we've got is the workforce, the experts who actually understand this asset, understand how it works. Historically, everybody who knows this has left at the end of the day, come back the following day. We need to make sure we can capture that information so we're not at risk of losing the expert knowledge over time that actually sits inside the minds of these engineers. So what we're finding generally globally is that we're getting more and more use, we're getting often lower investment, and that's leading to firefighting maintenance. So we're getting to a position now where what we can't do is simply do what we're doing already harder. We have to do something different. We have to work smarter. We have to start looking more at the condition of the assets rather than just looking at the age of the assets, understanding them in context, and from that making more informed decisions about doing the right work in the right place at the right time. All of this is focusing on data and digitalization in order to be able to support us in making those key decisions. The potential outcome and return on investment from digital operation moving towards a digital way of work rather than the more just time-based way to work for maintenance and replacement are potentially huge. So there are reductions in risk, there are reductions in cost for spares, increases in utilization. The critical number I would point out in this slide, though, is the up to 20% operations and maintenance cost reduction, simply by making sure that we're using all of the assets that we have optimally to do the best possible work that they can. The focus here very much is on making full use of the data that we've got in order to be able to support the decision-making process that we have. A good example of an organization that are doing this is New York City Transit. where what they're doing is they're bringing together and digitalizing all of the processes and workflows associated with a wide range of the assets that they're responsible for, and trying to move themselves away from a reactive world into a more proactive and predictive world to best utilize the resources that they've got and to increase the reliability of what is a critical asset for New York City. Without the infrastructure that they actually support, it's very difficult for the city to be able to operate properly. So we've talked about a few things here in terms of data and information. So I'm going to start by just defining a few terms to make sure that we're all talking the same language, communicating in the same way. So the key piece of terminology, if we're turning data into information, the first one is data. Data is facts and statistics. So there's no intelligence associated with them whatsoever. An example of a piece of data could be, I'm 6'6" tall. On its own, it's a piece of data. It has a certain level of quality. It has a certain currency associated with it, but it's not overly valuable to me in terms of what I can do with my day-to-day life. To start turning that into information, I then need to look at that data in context and add meaning to it. So if I take my first example, I'm 6'6" tall, I could say I'm in the top 5th centile for the region that I live in. So what that's doing now is taking that individual piece of data, comparing it to other pieces of data of the same type, comparing me to other people and the heights associated with them, and then adding meaning to it by adding in kind of geographic information as well. Once I've got that information in place, I can then start trying to draw and gain insight from it. And insight is the conclusions that we're actually drawing from the data and information. And it's these insights that drive action. So from the information that I'm in the top 5th centile might give me an insight that there are only certain locations I could go to be able to buy clothing, and that could drive action as to where I need to go or look up where I'd need to go in order to be able to actually get clothing that's going to fit me. So we're not here to talk about height or clothing. We're actually here to talk about, in particular, maintenance and the data and information associated with maintenance. So let's quickly run through what the types of data information that are typically used in order to be able to perform optimal maintenance. The first thing we've got is our maintenance standards, and these could be company-wide standards, they could be national standards, or even global standards, ISO standards that we're actually trying to work to, which will give us a target and a formal method of working. The second thing I critically need to know, especially if I'm trying to move to a condition-based maintenance regime, is what the current state of my asset is. What condition am I actually in at this point in time? And of course, I don't just have an individual asset, I've got an entire system out there. So I've got a whole load of different measures of multiple classes of assets, multiple instances of them, all of which have got a current state measure. And I've got the challenge there of how do I actually compare a measure that I'm getting from one asset to a measure with another asset in order to be able to understand the relative criticality of the state each of those assets are in. And this is where switching to information and the contextual side of things becomes vitally important to us. The next thing, if I want to look at maintenance, is what's actually the deterioration rate. So my asset is in a certain condition. Have I deteriorated rapidly to that state, or is it very gradual, or is it even a steady state that I'm in? Because it might be that if I'm trying to maintain optimally, I might not go to the area that's in the poorest condition. I might go to an area that's in a slightly better condition but deteriorating far more rapidly, as the other area appears to be stable and is still compliant at this point in time. It's often useful for me to actually have multiple deterioration rates for each class of asset, and if I have a real deterioration rate based on observations of the rate of deterioration of the asset and an expected deterioration rate based on theoretical models, then I can look at comparing the two of those, and that can give me additional information where I can gain insight in turn as to where I've got assets that are actually living longer or lasting longer than they should, and where are they deteriorating more rapidly than I would expect them to, so I can actually start doing some root cause analysis in those locations to try and extend the life of the asset. Context, I've already talked about. So this is being able to see the other assets that are around me. Again, we're looking at rail, which is my background, we're not looking at a set of completely unrelated assets that happen to be near to each other. There are complex interrelationships between all of these assets. So maintenance work on one asset could actually have a detrimental knock-on effect, unexpected detrimental effect on other assets. So we need to understand what's around us and what might be affecting the decisions that we're making or the condition scores that we're actually seeing. Maintenance history of my assets is extremely useful to me as well, as I can see deterioration that's happening. Did something happen? Was there a maintenance or renewal that took place that would actually explain a step change in the condition, either good or bad? So I can see how effective my maintenance strategy is actually being, but I can also see where maintenance work has been done that doesn't seem effective because I'm carrying on seeing deterioration rates in place. It's also useful for me to see maintenance history of contextual information of other related assets, either of the same kind or those near to me, so I can actually understand if historic knock-ons have actually had an effect on me, so that I can then go and firstly fix the root cause there, but secondly try and change the way that that maintenance work is done to prevent that work from happening in the future. So it's trying to learn from the past to optimize decisions that we make further in the future by using these multiple data sets, pulling them together in context, and then gaining insight as to why things are happening and how I can maximize life, which in turn gives me the opportunity to act. As constructed records can be extremely useful to me as well. I often like to think that if I'm talking about asset management, I'm standing on a timeline, and first thing I can do is look down at today's date. What is the condition today? Then I look into the past, and I'd like to see all of the measures of the condition of my asset that I've got and all of the interventions that have taken place, but right the way back from there to the as constructed record, so I can see what should be there in the first place, and maybe even the design intent further back from there. And then from that we can go on to the requirements as well. So that then gives me that complete history, and once I've got that information so I know what my condition is and exactly how I got here, it gives me it allows me to be more informed about what I need to do at this point in time, but also what may happen in the future, such that I can start planning and scheduling more effectively, again, to optimize not just what I'm doing today, but what I'm doing tomorrow, next year, and in 10 years' time. As an example of this, the image here is a little complex, but this was actually an analysis that was run where we were looking at speed data that was coming from multiple sources. So we had, and this is railway related data, so we've got speed data from the design speed associated with the length of track. We've superimposed on top of that speed data from the signposts, so what the signposts say the speed should be. We've done calculations against the geometry, the curvature, and the super elevation we have to work out what the acceptable speed range based on the current state of the asset is. And then we've actually loaded in data as well from typical driver profiles that are actually running over this length of track. When we combine all of those together, we can start trying to identify from the discrepancies between them not only where there are regions of increased wear or poor or rapid deterioration of the asset, but why it's happening and whether we should be going and improving quality of track, changing geometry, or maybe even going and training some of the drivers that we've got, or changing the posted speeds that are in place to be able to maximize and extend the life of the asset. We have other examples similar to this where people have pulled all this information in, but looked at historic rail replacements, so they can try and identify curves, rapid rail replacements in place, and then mapping that over to the driving styles and the design associated with the geometry to see what they can do to be able to extend the life of rails. So a lot of what we're focusing on here is actually talking about data. So data is our start point for being able to improve the quality of the information we make at the far end. So we need to have good quality data. Now, data quality are two words that I'm somewhat wary of because they grossly oversimplify what's actually quite a complex concept. There are a large number of different dimensions that we need to think about when we're actually considering the quality of data. I'm going to go through just a few of them now, but this is by no means a comprehensive list. The first is the accuracy of the data we're looking at. So this is how well a measurement we have, for example, matches what's physically happening in the real world. If we're having, if we have effectively built a digital twin of a certain asset, how well does it reflect what's actually physically there? The second is currency. So data, the instant we take a piece of data or record a piece of data that represents a physical asset, it starts becoming out of date the instant we capture it, and it becomes more and more and more out of date over time. What we need to do is make sure that the data that we have, or the currency of the data we have, is fit for purpose for the tasks that we are actually performing. There's no point in trying to keep a perfectly up-to-date data set that's in place for virtually any assets, and you could argue it's theoretically impossible to do so anyway, but making sure that if we need to know the condition of an asset on a daily basis, then we're no more than 1 day old in terms of the data set, the data that we have related to that asset, and the processes and systems are in place in order to be able to retain it with that level of currency. The next is completeness. This is, if I have a data set that represents something, does it represent every instance of that thing that I've got? If I'm looking at switches, or I'm looking at kind of roundabouts or traffic signals, something like that, do I have all of them in the system, or do I just have a subset? In particular, this becomes a challenge where we're actually in an asset that changes over time, and there are all sorts of systems. I would look at, for example, the ISO 19650 Part 1 and Part 2 standards, the BIM standards, something other people may know them as, which can actually tell us how we can flow data from design and from changes through into an operational space to make sure that the underlying model that we've had is actually complete and represents all of the assets. But then we need to make sure any other information, any condition scores and like we have, are also kept up to date up against those new assets. So it's completeness, but managing completeness through change control becomes a major challenge to us. Relevance as well. If we're talking about a large amount of data, we don't want to be collecting data for data's sake. What we need to do is look at why we need the data, what purpose it's going to be used for, and then focus ourselves in particular on the quality of the data we've got, on only that data that is actually relevant to us at this point in time. Of course, there are always arguments for actually getting additional data and running the what-if scenarios you've got going forward into the future, but our focus needs to be on what we need to do, what we need to be able to perform the tasks that we actually need to perform in order to maintain a quality asset. The final one I'm going to talk about is reproducibility, which is subtly different from accuracy. Reproducibility means if I measure the same thing multiple times, or I have multiple representations of it, do they match each other in turn? So accuracy is how well I map to or relate to the real world. Reproducibility is how well my multiple recordings actually relate to each other. A good example of that could be if I have a desk and I've got a yardstick and my desk is a yard wide, I can measure the width and I get a certain measure of it. However, if my yardstick is slightly too short, it's shrunk over time, I could measure 10 times and I get a reproducible score. So time and time again, I'm saying it's actually slightly over a yard, but it's not accurate because the measurement system itself I'm using has a quality issue associated with it. So we talked about data. The next thing I want to talk about quickly is big data, and this is a huge topic in its own right, and there are numerous wonderful conferences that I would recommend everybody attend talking about big data. So I'm just going to very quickly fly through the definitions that I tend to use. Originally we had the 4 V's of big data, then the 5 V's of big data, and now we're up to the 6 V's as the mechanism for remembering what a big data challenge is. The first of these V's is volume, the simple one. How much data? The more data we've got, the bigger the data problem that we've got, the data challenge, which is perfectly true. But while the volume of data that we're collecting over time is increasing, our capacity to be able to store that data is increasing as well, with cloud hosting being able to cope with the physical volumes that are in place. So generally we're keeping up as a rule by and large. Every now and again there are jumps in one or other technology that cause minor problems, but volume itself is often not the key challenge to big data. A bigger challenge is velocity, which is how rapidly is new data coming to us. Can we keep up with the rate that data's coming in? We have recording systems that can record terabytes per day now, and if it takes us more than 24 hours to process a day's worth of data, then we're going to get further and further and further behind in terms of being able to maintain our data set as being current. So keeping up with the velocity is actually the currency challenge that we face. Possibly the biggest problem in big data is veracity, which is how easy or difficult is it to reach into that data and start extracting information from it. Now things are improving here. Standards make a huge difference in terms of the formats for data and the content of data and consistency associated with it. But a lot of the legacy data we've got is stored in binary files that are very difficult to read and understand. So it becomes a challenge to reach in and especially get that data to relate it to other data sets so we can start maximizing the value that we gain from it. Variety is another challenge in big data. It's generally not a huge amount of one type of data. We've usually got lots of different forms of data collected by lots of departments all over the place to all sorts of different standards in different formats. And we need to ideally be able to bring those different varieties of data together to help us make more informed decisions. Value. Now, this is both the value of the asset, but the value of the data that sits in there as well. And I would suggest if there's one more thing that people take away from the talk that I'm giving here is that if we're moving towards a data-driven or a condition-driven view of maintenance, we have to think about our data not just as data about an asset, but as an asset in its own right. And as the fact that our data is an asset, it needs to be maintained, it needs to be kept up to date, it needs to be reviewed and assessed and cleaned from time to time and taken for refreshes to make sure that it is still fit for purpose for the task that we're using it for. And finally, visibility. There's no point in going through all of this process if the resulting information that you're getting isn't actually exposed out to people such that they can start gaining insights from the data that they're using. So we talk about this as big data, but if we look at this range of data sets that we've got and focus in particular on transportation asset management, then the different forms of data that we've got in different formats that we want to bring together to help make big decisions, we can also describe as a digital twin. And this is a big focus of Bentley at this point in time, is actually trying to push people towards having a living digital twin, an electronic representation of the physical asset, what's there and how it got there. That can be used in order to be able to both improve maintenance, but also run what-if scenarios and allow you to change things virtually rather than physically, so that by the time you get to the real world, you're doing things right first time. So looking at these different elements of big data, I'm just going to run a very quick example of that. This is actually measurement data. The exact detail of what measurement it is doesn't matter. I'll admit I've deliberately drawn it up to make it look as obscure as possible. But this is 10 repeat recordings of some measure of track geometry over a couple of 100 meters. There's all sorts of problems with this data. Each of the recording runs don't line up with each other. There's incorrect magnitudes of some of the peaks that are in place. So the first thing we'd want to do is actually start trying to improve the quality of the data in terms of its alignment, its reproducibility. And so this next slide here is the same data set that's been through an alignment process. So we can actually see now where there's a peak or a trough along the length of the track, which we measure in the x-axis. You can actually see where we've got change or growth or reduction in time. So this is actually improving the veracity of the data. We can start reaching in and getting information out of it as well by improving a couple of measures of data quality. The next thing we want to do is say this is useful to us, but I want to look at a higher level. I want to look at actually visualize how this asset is changing over time. So I create an index that represents this length of track, and then I draw it with the index measured in the x-axis and time in the y-axis, so I can see how it's changing over time. And I've just colored this up so that green is a nominal good quality, yellow is a nominal satisfactory quality, and then red in the future would be a nominal poor quality. Then I start bringing in other information as well, and the blue lines I've just pointed in are actually maintenance records. So this is looking at the variety side of big data. So I can now see how the quality, underlying quality of this asset has changed over time, and the impact that maintenance actions have had on improving that quality or not, as the case may be. After that, we start trying to extract further value from the data by predicting into the future from the last maintenance how we expect this asset to carry on deteriorating. And once we've got that prediction into the future for deterioration, we can then start working out where we go through maintenance and safety thresholds. And these are our dates where interventions are going to be required. And we can then start cross-referencing that to our maintenance plan or feeding this data back into our maintenance plan and our work order management system. We can then look at this in another way. So in this graph, we're seeing time increasing in the x-axis and our asset deteriorating in condition in the y-axis. And reading the graphs from the left to right, our asset deteriorated. The blue line shows the maintenance action. It carried on deteriorating and then predicted into the future to when we were actually going to need to actually perform interventions of different types and different severities. So this is a relatively simple example that shows us going from data with quality issues associated with it, resolving the issues that we can solve in quality, and then extracting successive levels of information from that data, finally bringing us to the point where we've got insight coming out of it that can in turn drive action, which is we know the date and we know the location at which interventions are going to need to occur, and we know we can look at the impact of not performing those interventions as well, which all goes towards helping us make more informed decisions. And then finally, we take that information and we can export it into work order management systems or whatever the next stage in the process, the workflow is going to be. An example of an organization that's doing this is actually Network Rail in the UK. What Network Rail are doing is they're actually bringing together data from 14 different systems, 65 data sources in all, and combining those and giving access to all of them to users not only in the back office but also on site, so that when they're out on site they're actually able to excuse me, they're able to look at the history associated with the asset, the maintenance history that's there. They can look at things that are invisible to them, like what's happening underneath the ground they're working on. And all of that is to help them both in the back office plan better maintenance and actually on-site implement better maintenance as well. The objective they had from linear decision support was to save 125 million Great British pounds sterling by the end of March 2019. The last number I heard, which was quoted by Network Rail Consulting for decision support overall at Network Rail, was a considerably higher number than that. So they are actually producing substantial savings from decision support processes. So what I'm going to do now is look at a couple of worked examples quickly. The first example we have is actually a road example. So what we're looking at here is about 130 miles worth of road. The key columns in here is the road schematic at the top, which represents the length of road that we're looking at, with significant bridges labelled across the length of it. The International Roughness Index, or IRI, if there's any road maintainers here, you'll be familiar with this. But what we're doing, international roughness, actually showing across the history of the changes over time. So the oldest survey in 2011 is at the bottom, and the newest in 2000. We're using old data because this is the data that we have permission to be able to show, because it's a little bit out of date. We don't have current data in the system. And then down at the bottom, we've actually got a maintenance history that shows us the date of the last maintenance that has occurred. What I can do is and once I've zoomed into that location, reference the maintenance history, so we've got an area that was in a poor condition there. Similarly, I can zoom into an area that's gone from red for poor to green to good condition, and I can actually see that that matches, in this case, over with a pavement improvement program that took place. What I might want to do, rather than just looking at the condition scores, is go to specific locations. So looking at, for example, an overbridge. So here I'm just selecting a bridge. I can jump to the location of that bridge and it'll show me the condition and the condition history. If I want a little bit more information, for example, I want to look at a GIS system at the same time, then I can simply open up a GIS system, and now I'm selecting from an asset register for an asset. It's jumping me to the linear location associated with that bridge and then pulling up the mapping at the corresponding geographic location. If I actually have more sophisticated data available to me, for example, a full 3D digital twin, then I can actually link that through as well, and link that through by the asset representing a bridge, for example, and then pull up the full 3D model, which in turn allows me to drill in and understand what's actually constructed and exactly what's there. So this is a nice example that's actually showing me bringing together data from multiple systems, from the roughness, from the asset register, from the maintenance records as well, and from the BIM models that have come from design and construction, and putting them in an environment that allows me to flick from one to the other to use the most relevant tool to be able to already drill in and query and understand what's actually happening to my asset. Again, all focused on helping to make more informed decisions based on understanding the past and the current state. A similar example in railways that we're looking at here. So this time we're actually looking at a link through to a CAD system. This is MicroStation, where we have a reality mesh representing an environment around a built rail network, and then on top of that we've put the as constructed drawing, which has got a viaduct with a single track on it with overhead electrification. The top right hand side is actually a schematic representation of the same piece of track, and in that we've actually got measurement data, and we've derived from that measurement data rates of change of geometry and the absolute condition of geometry. So we've got the as constructed, and then we've got the geometric changes over time that have actually been measured within the system. What I can then do, the middle center, that tabular list, is actually an extract from an asset register. I can select an asset from the asset register. It's jumping me to the geographic location, to the three-dimensional location, and also pulling up all of the maintenance history, the inspection history, and the changes that we're seeing over time. Again, all of this to pull together all these disparate data sets to be able to support us in making more informed decisions.